Hi, so I'm Subhadip Mukherjee. I'm a postdoc with Professor Carola Shanley, and what I will talk about is some of our recent works in unsupervised deep learning for image reconstruction in X-ray CT. So this is a typical acquisition setup in X-ray tomography. So you pass X-ray beams through the object of interest, and then you measure the attenuation profile. And from the attenuation profile, you want to reconstruct the internal structure of the object. So this is one typical 2D slice extracted from the CT scan. And then on the right, you see the corresponding projection data. So in the language of mathematics, you can formulate this problem as an inverse problem, where you have projection data y given by some forward operator, which is the projection operator here applied on the image, possibly corrupted by some noise. Yeah. So classically, people formulate reconstruction as a composite optimization problem where you have an objective with two parts. So the first part is the so-called data consistency term, which measures how well your reconstruction explains the data. And then you have a regularizer, which basically penalizes undesirable solutions, and it captures your belief about the type of solutions that you expect. And modeling these two mathematically requires respectively the knowledge of the noise statistics and the distribution of the image that you expect. So in recent years, deep learning has kind of changed this classical way of image reconstruction in CT. And depending on the type of data that you have, you might end up in one of these two settings, supervised or unsupervised. In the supervised setting, you basically have samples drawn from the joint distribution of the image and the data. And what you try to do is that you formulate your reconstruction operator as a parametric model, typically modeled using a neural network, which is denoted by f theta here. And then you minimize the average reconstruction error over the training data, possibly with some regularization on the weights. And some examples of this paradigm includes data-driven post-processing, where you basically first reconstruct using a model-based approach like filter back projection, and then learn a network to remove the artifacts from your model-based reconstruction. Or it could be algorithm unrolling, where you basically unroll an optimization method and replace different components of it using learnable units. So we are interested in the unsupervised setting precisely because it's difficult to get a large corpus of paired data in medical imaging, especially in CT. In the unsupervised setting, you basically have IID samples drawn from the marginal distributions of the image and the data. They're not necessarily paired. And you basically use the modularity of the variational approach, and you try to learn the regularizer based on the available data. And it can be done in many different ways. And two of the most notable ways involve data-driven regularization in an adversarial setting and pluggability matching. So I will show the results of some of our proposed approaches. So our approaches are the last two ones, the adversarial convex regularizer and unrolled adversarial regularizer. So in the first one, ACR, we model the regularizer through an input convex neural network so that you essentially end up solving a convex problem for reconstruction. And you can basically use guarantees, theoretical guarantees for, from the existing classical regularization literature. So as you can see, using ACR, you basically have a theoretically grounded method, although it's not computationally efficient, and because it requires solving a high dimension optimization problem, but it performs much better than PD. And then in UAR, the unrolled adversarial regularization method, we try to push the boundaries of unsupervised method by modeling the solution of this variational problem through an unrolled generator and train both the generator and the regularizer using an adversarial learning setup. And as you can see, you can pretty much get close to the learned primal dual, which is sort of the best supervised method for CT. And here is an example of limited angle CT, where you can see that structural constraints such as convexity on the regularizer, it helps reconstruct, for example, the highlighted region more faithfully without introducing any unnecessary, undesirable artifacts, unlike its non-convex counterpart and the supervised methods. So this brings me to the conclusion. So the take-home message is that we basically use this recipe of combining classical methods which come with theoretical guarantees with learning to develop methods which can sort of seamlessly leverage the power of data and still be provable. So we found that convexity helps stabilize the reconstruction for highly imposed problems such as limited angle CT. And we also showed that unsupervised approaches can be made competitive with end-to-end supervised methods, and in terms of both reconstruction accuracy and time. But yeah, I mean, we're still short of what supervised methods can achieve. So we need new ideas on that front. And all these methods, they are trained and tested on data drawn from the same distribution, and it's not very clear how their performance varies in case they encounter out of distribution data during reconstruction. So that requires both theoretical and empirical study. So yeah, that's all I had to say. Thank you.
Thank you. Our next talk is going to be by Anna Breger, and she's going to talk on image quality assessment for deep learning in medical imaging. Anna.
Hello, everyone. So I'm working here in the COVID project on X-ray